Okay, for this question, we're asked to find percent ionization, pH, as well as pOH of a 1.5 mole per liter solution of sodium acetate. So our first step is to figure out our modified Arrhenius. This is an ionic compound, sodium acetate, NH3, CH3COO. So the first thing that's going to happen to it is that it's going to dissociate in water to form sodium ions and acetate ions. Sodium is a spectator, so I know it's not going to do anything. It's the acetate that's going to continue to react. So CH3COOH plus water. For a modified Arrhenius, this is a base, so base is steel hydrogen. So we're going to produce the conjugate acid, which is acetic acid, and hydroxide ions. If we set up our ice table, we don't put the liquid water in there, we can start filling in the information we're given. So this is the concentration, 1.5 mole per liter of sodium acetate. If I look at my dissociation equation, it's balanced at a 1:1:1 ratio. So that's also the concentration of the acetate ions. So the concentration here, 1.50 mole per liter, is the initial concentration of my weak base. Initially, I'm not going to have any hydroxide or acid, but once they react with water, we should see an increase in the products. Because I don't know what the final pH is, or pOH, I don't know what the mole per liter concentration of hydroxide is, so we're going to just assume that it's X. These are a 1:1 ratio, so they're going to be equivalent. My weak base will decrease by the same amount. So these will increase by X. This also has a coefficient of 1. So a 1:1 ratio will decrease by X. So we're left with 1.50 minus X. Just like with weak acids though, a lot of times this change is so minuscule that we can ignore that. So we figure that out if we check the rule of 1,000s. We take concentration of weak base and divide it by Kb. Kb is not given in our data book on page 8-9, so I've got to figure out what Kb is first. Kb is equal to Kw over Ka. Kw is 1.0 times 10 to the minus 14. Ka is the value of our conjugate acid. So we're going to look for the Ka value of my conjugate, which is acetic acid, and that has a value of 1.8 times 10 to the minus 5 for the Ka. This gives me a Kb of 5.6 times 10 to the minus 10. So if I sub that in, 1.5 mole per liter, divide by Kb, 5.6 times 10 to the minus 10, I get a huge number that's like times 10 to the positive 9. So because this is way greater than 1,000, this means we can ignore X here and assume that initial and final concentration of our weak base are equivalent. Since the change is so minor, we can ignore that change. So now we just need to figure out what X is. So if I'm solving for X, I set this up as Kb equals products over reactants. I already found Kb by dividing Kw over Ka. So this will be 5.6 times 10 to the minus 10 equals, my products are both X, so X times X gives me X squared, divided by my reactant concentration of 1.50. When we do that and rearrange to solve for X, we get X equals 2.87 times 10 to the minus 5. So since X equals 2.87 times 10 to the minus 5, I know that's also the concentration of hydroxide. So I can use that to find pH and pOH, because hydroxide equals 2.87 times 10 to the minus 5 mole per liter. pOH is negative log of the hydroxide concentration to give us a pOH of 4.54. I can find pH by subtracting that from 14. Oops. 4.54 to give me a pH of 9.46. The final thing that it asked for in the problem was the percent ionization. So what that means is, of these acetate ions that reacted, what percent of them actually reacted to produce hydroxide? Okay, so what we do to figure out the percent ionization is we take the amount of hydroxide that was produced and divide it by the initial concentration of our weak base. We can do the same thing for weak acids by taking the hydronium concentration and dividing it by the initial. If it's a strong acid or strong base, it's going to be 100%. Hydroxide concentration would equal the concentration of the base. For weak acids and bases, it's not. So I'm going to take percent ionization is equivalent to my final concentration of hydroxide divided by the initial concentration of my weak base times by 100 to convert that to a percent, and we get a very small number. It's actually 0.002%. So that means very few of those acetate ions are actually going to react to produce hydroxide.